Hi, in this video we're going to go over section 15.4, which is all about the applications of double integrals. So in general, all of these applications can be summed up with the idea of a density function. So for instance, we're gonna look at mass density. This could be any kind of density. I'll talk about that in a second. If a lamina, now we're going to start with this weird vocab word. A lamina is going to be an infinitely thin 2D shape. So lots of things are approximately lamina because they either have a pretty uniform shape and a very thin thickness. Like a sheet of paper is a good idea of a lamina. But this idea will be extended into 3 dimensions as soon as we have 3 integrals. But right now we have 2. So lamina is a 2D shape, probably infinitely thin is how we're thinking of it. If we have a lamina with a mass density, has a mass density of rho, it's a Greek letter rho, x comma y. So an idea, if it's hard for you to picture what this is, it's measuring kilograms per meter square. How much mass is in each square meter of the surface, of the grass sod, of the paper? Then this double integral over the size of the lamina, where d is the lamina, rho xy times dA, is the mass of the lamina. So rho is the mass density function, d is the lamina, d is the lamina, dA would be a tiny change in the area as your normal thing, equals area, d area. So what are we getting here? We're getting like rho xy times dA is kilograms per meter squared times meters squared, or meters times meters. And what you're going to be left with is the mass. So that makes some sense. Now, this rho does not just have to be mass. It could be charge, could be a charge density function, it could be a temperature density function, finding the temperature at each point in the field, in the piece of paper on like a hot plate maybe, for instance. So there's lots of things that rho can represent, and anything that rho is will change our interpretation of the integral. Just like we have an idea that a 1 integral, 1D calc, can represent area, but it can also represent the mass density of a chain or of a string or anything else, depending on what we think f of x represents. If f of x was cross-sectional area, then the 1 integral could represent volume. But as we've seen, volumes is usually better suited to a 2D function. Likewise, if we take another concept from physics, would be the first moments of mass. And again, this does not have as good of an analogy with charge or something, but this is important for the biggest concept we can use here and develop here. So a moment is the tendency for a lamina to rotate about an axis. Specifically, m sub x is the tendency to rotate about the x-axis. Surprise, surprise. It's going to have a weirder formula than you might expect. It'll be m sub x is going to be the double integral over the lamina y times the mass density function. Because y is your measurement for how far you are from the x-axis. Okay, that should make sense to you. I'll draw a picture in 1 second. dA. So if I had a 3D coordinate system and I had a rectangle floating out here, we're going to do an example just like this. If I want to measure its tendency to rotate about the x-axis, we want to think about how these distances are going to affect the rotation. And surely each of these distances can be best measured by the y coordinates of their distances. That's a good idea of how far we are from the x-axis. And that should make some sense to you intuitively. If you hold an object further away from your body, let's say that x-axis is our body here, then that's harder to hold up than if you hold it close to your body. Right? Like the mass as we go further out should increase its moment. Whether that makes sense to you or not. Like that's how balancing works though, right? We want to find the right place to balance things. It's going to be our main idea with center of mass. Spoiler alert. M sub y will be the tendency to rotate about the y-axis. And its formula will also be a little confusing. There we'd use the x times the rho xy dA. So then if we divide out by the mass, which I'll just write down to recall, is the double integral over the lamina of just the mass density function with respect to area, the center of mass, or C.O.M, not .com, but close, would be the point where all mass seems to be concentrated. Now, that's a very vague definition, but I think we understand this. It's where the object is balanced. That's a good way to understand it. When we talk about balancing an object, we know all of its mass isn't existing at that one spot where it's balanced. But the object's behaving as if it is, right? If I balance a ruler at the tip of my finger, I know there's mass at both ends of the ruler, but I'm able to support it with almost a single point in space because the moments are balanced out. Now, here's the one last confusing bit. Or perhaps things become a little more clear. It depends on how you see things here. X bar is going to be the moment with respect to y divided by the mass. Right? Because that would just leave the x around. That would just leave the x. That's one way to remember it. And y bar would be the moment with respect to x divided by the mass, because that would just leave the y. So again, it's a little confusing. This guy divided by the mass part, so to speak, is going to tell you the exact y coordinate to balance things around, because that's the axis where this thing naturally wants to rotate. M sub y is telling you the exact x coordinate to balance around, because that's the x-axis that things want to rotate along. So if you take both of those points, you get a perfect mass center. So the center of mass would be the point x bar, y bar. It's probably good to look at an example of this. So find the center of mass of a lamina with mass density function rho of xy equals y. So if I have coordinates 5, 3, the mass of that point is just going to be 3 kilograms per meter squared, per square meter. And a point of 3, 7 is going to have a mass density of 7 kilograms per meter squared. So find the center mass of a lamina with mass density function that, and occupying, so an infinitely thin sheet occupying the region between 0, 0, 3, 0, 3, 2, and 0, 2. So 4 points. Let's draw them. 0, 0, 3, 0, 0, 2, 3, 2. We have a rectangle. Okay, and this is our lamina. Now, before you get going and thinking like, oh, this is easy, it's just right here. That would be true if the mass density was normal, let's say. If this was a normal situation where the mass was just exactly the same at every single point. This function is saying the mass density is not going to behave like that. That things are going to get more valuable, more mass, the farther away we get along the y-axis. Now, that doesn't necessarily matter for our first step. Our first step should just be to find the mass, which is the double integral over the region, which is a rectangle, just the mass density function, dA. You should have enough technology at this point to find this integral. So please pause the video and evaluate this integral. 3, 2, 1. I'm going to go 0 to 3, 0 to 2, y. You should be able to tell which one did I do first. dy, dx. Because these are the y bounds. It's pretty clear, going from 0 to 2 on that axis. Now this is a rectangle, so if you went really fast, you could have broken it up by the dx stuff and the dy stuff. Getting x evaluated from 0 to 3 times 1/2 y squared evaluated from 0 to 2, or 3 times 2 with a mass of 6 kilograms. Now that happens to be the area. If the mass density were 1, that would definitely be the area. If the mass density were x, I don't know for sure. But if the mass density was sine of y, would we expect the mass of this to be equal to the area? No. So please do not make silly assumptions like the mass will always be the area. It just happens to be in this example. Now, to find the center of mass, we're going to compute the moment along the x direction. So this is going to help us find the y that rotates along. Again, it's a little confusing. It's y times y dA. Okay, this is trying to help us figure out the y-axis of rotation. How high along the y-axis do we rotate freely? How far from the x do we go? So, if you were careful, you would get pretty much the same thing, dy dx. You could break it up the same exact way because it's still a rectangle. I'm hoping we don't get too cluttered. X from 0 to 3, 1/3 y cubed from 0 to 2, 3 times 8/3, or 8. Now, right now you could compute y bar. We're just going to save it at the end so we don't get confused. M sub y is going to be the exact same integral in terms of the region, x times y dA. You try that one. Pause the video right now, try to evaluate this, see what you get. 3, 2, 1. So there's no way to simplify it right away, but you can break it up. X dx times the integral from 0 to 2, y dy, 1/2 x squared from 0 to 3, 1/2 y squared from 0 to 2, evaluating out to 9/2 times 2, or just 9. So the center of mass is x bar comma y bar, or m sub y divided by the mass, m sub x divided by the mass. Or in this case, 9/6 comma 8/6, or 3/2 comma 4/3. What does that correspond to about the rectangle? Well, I'm going to go 3/2 out along the x. So that is exactly halfway through the rectangle, or as close as I can get it. And then the y bar is telling us to go 4/3. Now that's more than half, right? Half would be here. Nope. Half would be down here, but it's higher than that. Why did it shift slightly higher than that? Because there's more mass at the top, toward the top end of the rectangle. It's not all the way at the top. Maybe I drew it a little too high, but you get the idea. We have to hold it higher on the rectangle because there's more mass toward the top of the rectangle, because that's how the mass density function's weighting it. The y coordinate matters more, or is the only thing that matters in terms of generating mass on an object like this. Okay, let's try another one. Find the center of mass of the lamina with mass density function rho of xy. It's just going to be x this time, because we can't make it too complicated or else it's just going to get wild. In the region given by a triangle with vertices 0, 0, 2, 1, and 4, 0. So your first goal is to very carefully try to find the region, decide how you would want to integrate it, because our first step is going to be to find the mass, which is a double integral over the region of the mass density function, which in this case is just x. But either way, we want to change this to an iterated integral. So the first thing you have to do is find the shape. Try to graph it, try to go as far as you can. Maybe you can even get the mass, and unpause the video if you get stuck or need a hint or just want to check your work. 3, 2, 1. So I'm going to draw my shape. 0, 0, 4, 0. And halfway between that, 2, 1. So it's not going to look perfect. This kind of shape, I don't want to use top minus bottom, because that would require two different formulas. Instead, I'm very much wanting to use the left minus right idea, meaning I want to get x values. So if you haven't done so already, give me x equals equations for both the left and the right boundary. You may have already found y equations, but you can't use y if we're doing left minus right or right minus left. So for the left side, I'm getting x equals 2y. If you add y equals 1/2 x, that is also correct. But again, we want x values. And for my right side, I'm getting 4 minus 2y. And right now I'm just triple checking that that's correct, because it would be a shame to waste any more time on this problem. So that's going to leave us with the idea that we want to do our x first. So if I'm going to try to do my x first, I want to set up an iterated integral, x for the mass density function, then dx, then dy, because I want to do these x values first. The left bound on the bottom and the right bound on the top, and the y's all the way on the outside. Now, our first step, integrate the x. Go from x equals 2y to x equals 4 minus 2y. Still with respect to y at the end. 1/2 4 minus 2y quantity squared minus 2y squared dy. If you simplify that, you should get 8y minus 4y squared after you integrate, which is of course the number 4. So that's the mass of this region, which is not, to be clear, it's not the area, because the area of that triangle is 2. So now we want to find the moment in both the x and the y direction, the x-axis moment, which will help us find the final center of mass. So this is y times the mass density function. But for the most part, this integral is going to be very similar. We're still going to want to iterate it the same way we just did. And in fact, even with that extra y there, that ultimately won't affect the process. If you're unsure what I'm saying, you should go ahead and try it out. But I'm saying because this y is a constant and we're doing x first, I'm going to end up getting back to here, because this y shouldn't affect anything for our first integral. So please feel free to check and make sure you're getting 8y minus 8y squared once you do that whole first integral. That trick does not always work. It will not work when we find the moment about the y-axis, for sure. And so I'm getting 4y squared minus 8/3 y cubed, all from 0 to 1, which is 4/3. One last thing to go. Let's find the moment about the y-axis. X times x dA. Which would be 0 to 1, 2y to 4 minus 2y, x squared. And again, do not think you can use the same exact trick. It will very much ruin your night. So 0 to 1, 1/3 x cubed. This time from x equals 2y to x equals 4 minus 2y. So very similar to what we just did back in the math step, but that extra cube means it's probably easier to use a reverse chain rule or u substitution than it was in the blue mass integral. And so what we're getting here is going to be negative 1/24 4 minus 2y to the 4th minus 2/3 y to the 4th, all from 0 to 1, which is, of course, negative 2 to the 4th over 24 minus 2/3 minus negative 4 to the 4th, over 24. I'm going to shrink it and simplify it. Just 28 thirds. So our center of mass at the end of the day, x bar, y bar. Remember, this is still a little backwards if you're just getting used to it. It's this formula. So we're going to get 28 thirds divided by 4 is 7 thirds. 4 thirds divided by 4 is 1 third. Which corresponds to roughly where I put the horizontal line I did, but 7 thirds is a little bit shifted over in the x direction. Which is again what we would expect because our mass density function says this guy weighs more in the x direction. One more example with a different kind of density function. Find the total charge of a plate. So again, a two-dimensional object. Again, not really, but we can imagine it to be, with charge density function. So that one word just changes it. Charge density of, we usually use sigma for charge density. It really doesn't matter what letter you use. Obviously, you have to keep it Greek to keep everybody confused. X squared plus y squared, all under a square root. And the charge is spread, or the plate is shaped, however you want to think about it, across x squared plus y squared equals 4, and y equals 0. So we're just talking about the shape of this plate is the half circle, x squared plus y squared equals 4, and y equals 0 is this line. I guess these should have been inequalities. So x squared plus y squared less than or equal to 4, y greater than or equal to 0. That's the disk I'm talking about. So it's a disk. So it might be better, especially with this kind of charge density, to instead of doing our function charge or capital Q sometimes, which would be this, which is a very gnarly integral to work with, is to convert this to polar. So to review the last video, why don't you go try to convert this function to polar? You'll have to convert the integrand to polar and this region in polar. Take your best shot at it. Unpause the video if you get stuck or if you want to check your answer. 3, 2, 1. So the region is very much r going from 0 to 2, theta going from 0 to pi, all the way to the other x-axis. So 0 to pi, 0 to 2. And we're going to have root r squared, r dr d theta. Did you forget this r? Super easy. You got to watch out for that trap. But once you get rid of all that, this is actually a quite simple integral you have for yourself. R squared dr d theta. It's so simple, it's even rectangular, and you can break it up the way we like to. Getting theta from 0 to pi, 1/3 r cubed from 0 to 2, or 8/3 pi. And that would be the charge of that plate. So overall, a really useful branch of math in terms of finding lots of little physical quantities. Hopefully that makes sense. Please try out the homework, and I'll see you in the next video. Thanks for watching.